Hi class, welcome to the second half of lecture today. So we're going to talk now about the Exoplanet Catalog, the entire list of planets and planet candidates that we've discovered. As we've talked about over the course of this quarter, this is really a remarkable time that we lived in, because if you go back in time, certainly to when I was a kid and to a little bit of the time before most of you were born, we did not know of any exoplanets around any other stars. The only planet we knew any planets lived around was the sun. And so this is really a remarkable time that we live in. Our understanding and knowledge of exoplanets is growing exponentially as we discover more and more planets all the time. There is a wealth of data and a wealth of things and mysteries that we are trying to understand and discover. And we'll talk about some of that next lecture. So on the screen behind me here is a famous representation of the Kepler Exoplanet Catalog. This is called the Kepler Array, and I'm going to show you another version of it during lecture today. But basically, we were making these as the planets were discovered by the Kepler mission to show the diversity of planets that we were discovering, both in terms of the sizes of the planets themselves, the temperatures that the planets experience, and their separations from their parent stars. So this is an example of one of these things called Kepler Array. If you go search for this on YouTube, you'll find all the successive iterations of this have been developed. And I'll show you one of the more recent ones as part of lecture today. Okay? Okay, so let's go ahead and start a few slides. So the first half of lecture today, we had talked about exoplanet search techniques, and we said that those all very robustly depend on the properties of the planets themselves, as well as the properties of the star and the technology that we're actually using. So some techniques are much more sensitive to planets than others. Some techniques are very sensitive to giant planets. Some techniques are very sensitive to smaller planets. And so most of the planets in the Exoplanet Catalog have been detected by the transit method. And so you see here in this image, planets very close to their parent star, transiting the parent star. And that's how most of the planets in the catalog have been discovered at this point. So I'll show you the current catalog. The exact numbers in the current catalog depend on where you get it from. So I'll give you links to several catalogs if you're interested in exploring them. We'll talk mostly about Kepler and Tess and how they've gone about looking for planets using the transit technique. And then at the end, I'll point you to a couple of interesting planetary systems that you probably have heard about in the news if you follow this at all. There are lots and lots of exotic and interesting exoplanet systems. And so we could spend days talking about all the interesting systems that we've discovered. But I'm going to tell you about these two because they're two that have garnered a lot of interest. Okay? So the Exoplanet Catalog, when you talk about the contents of the Exoplanet Catalog, you do have to look it up, even if you're talking about it only weeks or days apart from each other. The data for like the Kepler mission is in the can, as we say. It's been recorded. Kepler is no longer flying, but it's an enormous amount of data. And so it takes a lot of time to process it and search for it and decide what it is that you're looking for. And so we are still analyzing Kepler data. We are still discovering new exoplanets in it all the time. There are a couple citizen science projects associated with that. So if you go to, I think it's planethunters.org, Planet Hunters at the Zooniverse, they're using folks just like me and you to look for exoplanet transit. So it changes all the time. And in addition to missions like Kepler, we're still using all the other techniques that we described from ground-based telescopes to look for exoplanets. So the number of exoplanets is just constantly ticking up. Okay, but I went today, as I was preparing slides, to each of the catalogs to write down the current numbers in the Exoplanet Catalog. So the two primary ones that people often use are the one at NASA there, exoplanets.nasa.gov, exoplanet-catalog, and then the one in the European Union. And so that's at exoplanet.eu/catalog. Okay, so you can see there we have confirmed planets, we have candidates, and then we have a column for systems. Okay, and so the differences there are confirmed planets are planets which have been detected by one technique. say, transit method with Kepler, and then they've been reconfirmed by other observations. So we followed it up from the ground, or we did a second run of transits, and we have better transit data than we did before, and the signal is very strong. We're confident it's a planet. Candidates are systems where we've seen maybe only one transit, or we've seen something that looks like a transit. It's still kind of fuzzy in the data, or we need to do follow-up observations. There's all kinds of candidates. And the candidates, largely the number of improved of confirmed planets is going up by changing candidate planets into definitive, yes, we're sure this is a planet, and moving it to the other column. We're still adding new planets into the mix all the time, but lots of these candidates are being moved over as confirming observations come online. The discrepancy here between the confirmed number of planets and the number called systems is indicative of the fact that we now know and are discovering more and more systems with multiple planets in them. When we first started this, we were discovering one planet at a time around one star, and we didn't know, at least based on observations, that there were other planets in that star system. But today, there are certainly lots and lots of systems where we know of multiple planets in them. Okay? So down there at the bottom, exoplanets.org, they're not updating that site anymore, so the numbers aren't climbing, but they have a lot of really nice tools for making plots of the planetary properties and stuff. So if you're interested in exploring kind of what the distribution of orbital periods versus orbital eccentricity is, or what's the orbital period versus mass, you can make all these nice plots, and you'll just use the whole catalog and make really great plots for you. So many of these sites also have associated apps on your phone, so you can also play around on your phone with the exoplanet data, and I think exoplanets.org is one of those that has one of those apps. The last link there is to openplanetcatalog.com. If you go there, that is an open source catalog. So they pulled all of the data from the space agencies and compiled a complete exoplanet catalog that is on GitHub. So many of you may know GitHub is a system for managing versions of data and managing versions of software. And so this is a great site to use if you play around with data a lot, because it documents all the issues, all the errors, and all those sorts of things that they found in the data as they process it. You can check out your own data. You always know exactly what version you checked out. And so on. So that's another resource for those of you who like to tinker around with programming and data analysis on your own. Okay, so that's the exoplanet catalogs. I do a public lecture on exoplanets very often, and every single time I go to NASA exoplanets and I update the number, that number climbs up. And so it's definitely something that you can track over time. The number of exoplanets constantly is continuing to grow. So most of those planets, lots and lots of those planets, came from a mission called Kepler. So this is the Kepler Space Telescope over here on the right. It was not the most enormous telescope in the world. It was much smaller than Hubble, but it was designed with a very specific purpose in mind, and that was to measure the transits of exoplanets by looking at the same stars over and over and over and over and over again. So the mission was aloft for 9 years. They observed in 2 fields because they had a gyroscope fail, and so they had to, they observed the original field, I can't remember for how long it was, and then the gyroscope failed, so they couldn't point the telescope where they used to point it, and so they started observing a different field. So we have 2 Kepler fields on the sky, and all of the Kepler data comes from those fields. Over its life, Kepler observed some 530,000 individual stars. Okay, so that's a lot of stars. I'll show you the star field here in a minute. And what they did is they just measured the brightness of the stars over and over and over again, and they plot the brightness of the stars versus time. So in this graph here at the bottom, look at the top line there. You'll just see that little smattering of dots, okay? So that is the brightness of the star over time, and you'll see the dots are kind of up and down a little bit, but every now and then you see one that's low, okay? And then the dots are kind of all around. And so the job that we have as astronomers is taking that data, which is really dot, 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 okay, and then folding it on top of itself so you get a plot like you see there in the top with all the dots lined up on top of each other. okay? Now, what we do is we fold it differently every time. Sometimes we fold it down so it's 1 hour on top of each other every hour. Sometimes we fold it so it's 2.5 hours on top of each other all along. And we do that for all kinds of different folding times. But if you happen to fold it at exactly the orbital period of a planet, you get a curve like the one that's there on the bottom. So this is folded at a little bit more than 8 hours. Okay, and you can see that if you fold it at the exact orbital period of the planet, what happens is every time the planet's in front of the star, your dot, your measurement, gets folded into the same place on the graph. And so it makes a very accurate representation of that transit curve. So this is the way we look for exoplanets. We take all those 530,000 stars and all of the little dot measurements that Kepler made of the brightness, and we just fold them at different times until we see these individual bright transit curves that you see there with the red and the black dots there in that lower graph. Okay? So that's how it works. So Kepler started by observing we call it the Kepler field. It's in the constellation Cygnus. So if you go out at night right now, right when it first gets dark, kind of 10:30ish or so, Vega is the brightest star you'll see in the east, just a little bit north of east in that part of the sky. The Milky Way is just rising there. So if you wait till midnight, this will be higher up in the sky. But that's the area of the sky where the Kepler field is, okay? So Vega you see marked there, but you'll also see two other stars, Deneb and Altair. Those are the three brightest stars that you can see in that part of the sky, and you can see those even if you live in Chicago. They form what's called the summer triangle, okay? And the Kepler field is right there on the edge of the summer triangle. Okay, so you can see it's kind of in the direction of the Milky Way, but it's not in the thick of the Milky Way. So we're getting lots of stars, and that provides us the opportunity for lots of planets that we, lots of systems that we can look for planets in. Okay, so the summary of the Kepler data can be made in a variety of plots. So this is probably one of the most common ones you see. So plotted on the vertical axis is the size of the planet. Okay, and so you'll remember that the way we determine the size of the planet is we watch the planet go around the star, and when it goes in front of the star, the light from the star dips down. And how much the light of the star dips down tells you the size of the planet. If it's a big planet, the light dips down a lot. If it's a small planet, the light dips down just a little bit. Okay, so plotted vertically is the relative size of the planet compared to Earth. Okay, so 1 there is a planet that's exactly Earth-sized. Okay, so 4 there is roughly Neptune size, and just a little bit more than 10 there is Jupiter-sized. And then plotted across the bottom is the orbital period. How long does it take the planet to go around its parent star? Okay, so this is what's called a logarithmic plot, so things are not evenly spaced. But if you go back, we talked about logarithmic plots in the math lecture at the beginning of the quarter. So the spacing is not quite even. So over here, more than half of what you can see here in the plot has orbital periods less than 10 days. Okay, that's on the left side. But the Earth, if it were on this plot, would be right there inside that red circle. And you'll notice quite conspicuously that there are no planets yet that we've discovered in that part of the diagram here. But there are lots of planets that we've seen that are Earth-sized. They just are in orbits that are much, much faster than the Earth's orbit. Now, part of that is the fact that they are, we've discovered that many planets are around what are called dwarf stars. So those are those red M-type stars that are down in the bottom of the main sequence. And most of those planets, they can be very, very close to their star. And so lots of these stars, lots of these planets that you're seeing here in this Kepler sample are related to the being around M dwarfs, okay? In the kind of purple and blue are other discoveries that have been made by other techniques, both before and after Kepler. You'll see most of them are centered up there around the Jupiter-sized planet line. That is indicative of the fact that most of the other techniques rely on the planet being pretty big, so that it has really big influence on the star if we're going to see it from our ground-based telescopes. So Kepler is really good at seeing smaller planets, which is why we flew Kepler in the first place. So here is the modern Kepler Array that I promised you I would show you. So this was made by Ethan Cruz. And so if you go to YouTube, you can certainly find this Kepler Array. I put the link for you up there at the top if you want to go watch it. It has pretty music, so you can use it soothing in the background while you're doing homework or something. Let me point out a couple of things for you here before I actually go ahead and play the movie. So look at the dashed circles that you can see here in the initial image. So those are the orbits of the planets in our solar system. So right near in the center of the image there where it says solar system, those are the 4 inner planets. That's Venus, Earth, Mercury, and Mars. In proper order, it's Mercury, Venus, Earth, and Mars. Okay, and then the kind of big dash circle that you see there is Jupiter, and the outermost dash circle you see there is Saturn. So if you look at those, right, so if you look there, you can see little blue dots on those inner dash circles. So that is the location of the inner planets of our own solar system. Okay, so what the movie's going to do is it's going to play, and it's going to show you how all of these planets are orbiting as a function of time. So if you want to compare it to our own solar system, just watch that inner dash circles. You'll see our planets going around, and what you'll see is lots of the planets are whizzing around their parent star really, really fast compared to the planets in our own solar system. All of this is to scale, so you'll notice many of these systems are very small. We said that as well. They're much closer to their parent star than the Earth is to the sun. And then the color of the individual dots tells you the relative surface temperature of the planet. And that's based on the sorts of things that you and I have been talking about, which are how much energy is the parent star delivering to the planet, and what do we think the relative influence of an atmosphere on the planet is. We can, for planets where we can actually see light from them, we can actually measure the temperatures, but these temperatures are based on modeling in some cases. Okay, so let me go ahead and play the movie, and you can watch things start whirling around. So you can see lots of these planets are whirling around their parent star really, really quickly. You can see the planets there in our own solar system going around at normal rates. So these are all happening very, very quickly on the order of days. There are lots of multi-planet systems, which we said at the beginning here. In fact, I think all of these are just the multi-planet systems in the Kepler data. So we're scrolling out there. So we're now out the outermost circle. You can see there is the orbit of Uranus. And you can see that we have yet to discover a planetary system that is as large as our own. We've never seen a planet as far out in a planetary system as we see Uranus in our own solar system. That's not surprising because all of the techniques require you to watch these systems for long periods of time. Uranus has an extremely long orbit, and so it takes a long period orbit. So it takes a long time for it to influence the star in a way we might notice, or it takes a long time for it to transit in front of its star if we were happen to be looking for it for a transit method. It's also very hard to line up a planet like Uranus as far away from the sun it is in a transiting system. Okay, so that's the Kepler Array. You can certainly go play it on your own if you want to watch it on YouTube. So this is Tess. So Kepler ended in 2018, and Tess is the next planetary satellite used for looking for exoplanets. It's the Transiting Exoplanet Explorer satellite. And Tess is doing more or less the same sort of thing that Kepler did. It's basically looking at stars over and over again and watching for transits. But it's doing it slightly different than Kepler did. Instead of watching the same field over and over again for a decade, Tess has many different fields that it's looking at, and so it's trying to look at stars all over the solar neighborhood, and it's going to do this for 10 years, not for 10 years, for 2 years, all over the entire sky. Okay, and so what we're really doing here is we're just trying to understand what is the distribution of planets in the local solar neighborhood. We're looking at all the nearby stars, and we're going to start getting the census for planets all around us rather than just the census for planets all in that direction in the sky. So the expectation is when all is said and done, some 20,000 planets will be discovered by Tess. All told, that we expect, based on what we're seeing already from Kepler data, that maybe 500 of those will be smaller than Earth. Okay, and there will be dozens, we don't know how many dozens, but dozens we expect that'll be roughly Earth-sized, and then some 17,000 of them will be larger than Neptune. Okay, with all the rest adding up to 20,000 scattered somewhere in between. We don't know what those final numbers are yet. Just like Kepler, we'll have to analyze the data. It will take a long time to do that, but this is the expectation. So Tess has been up just for a little while now. I'm sorry, I should have looked up the launch date before lecture, but I forgot to. But so far, the data has 46 brand new exoplanets, so those have come from Tess, but we have 1,800 candidate planets that need to be confirmed. Okay, so Tess is definitely starting the discovery engine. We're putting more planets on the table, but we have to go back and do all those confirming observations. But the number here from Tess is rapidly approaching 2,000, so we're well on our way. Okay, so this will be the big news when you come back to Northwestern for homecoming in 4 or 5 years, or you just want to drop in Northwestern and have a Dr. Pepper and a pizza with me and we can talk about exoplanets. We'll know a lot more about Tess when you come back after you graduate. Okay? Okay, so let me tell you just about two kind of interesting planetary systems, and then we'll call it a day today. So the first one I want to talk about is Proxima Centauri b. So Proxima Centauri is certainly the most interesting star to us because it is the closest star to the sun. And the reason that's interesting is because it is plausibly the only star that we could easily, for some definition of easy, send a space probe to. There have been many proposals for how to do this. Some of you may know of a project called Starshot. That's an example of a recent kind of exotic high technology proposal, but there are other proposals that we've talked about as well. And so the last week in class, we're going to talk about extraterrestrial intelligence. And so part of those discussions, we'll spend the day talking about starships and travel to other star systems. And I'll tell you a little bit about trying to get to Proxima Centauri when we do that. But it is the closest star to the sun. And so we have looked and discovered an exoplanet around Proxima Centauri. It's called Proxima Centauri b. And so this planet is not that much bigger than the Earth. It's about 1.6 times the mass of the Earth and about 1.3 times the radius of the Earth. I'll leave it to you to go calculate what the surface gravity on that planet is. It is very close to its parent star. So it's got an orbit only 11.2 days long, okay? But Proxima is one of these red dwarf stars. It's type N5. So you can calculate what the habitable zone for that is. And it may, actually I should know when I don't know if Proxima Centauri b is in that habitable zone or not. Okay, so this is really quite interesting to us because it is the closest exoplanet that you and I have any hope of ever really visiting. All the other exoplanets are in star systems. They're much, much farther away. It would take forever to send the space probe to them, even longer for the data to get back to us. And so it's unlikely that we will ever do anything more than look at those systems in telescopes. But Proxima Centauri b is just close enough that we can imagine it might happen. Okay, it may not happen in a single human lifetime. If we started today, it may not happen till you're 95 years old, but it could in principle happen. And that's the reason I think most people find this interesting. The second system I want to tell you about is one called Trappist I. So Trappist I is once again one of these red dwarf systems. Okay, so it's a type M8 on the main sequence. It's about 39.6 light years from the sun. But the thing about this system is that we have discovered 7 terrestrial-sized planets around this star. And 6 of them are very likely in the habitable zone for that star. So that is remarkable. You and I have talked about our own solar system, and there are 2, 3 if you want to be generous to Venus, planets in the habitable zone of the sun. And you may remember from the very early part of quarter, when we talked about the Drake equation, one of the things that goes into the Drake equation is how many planets are in the habitable zone. okay? So we put a number in the Drake equation based on our experience in our own solar system. Well, here comes Trappist I, and there are six planets in the habitable zone. And so that is very intriguing, because one of the things we really want to know is, how common is that? Is it likely there are lots of planets in habitable zones, or is it likely there aren't very many planets in habitable zones? That's an important question for us if we're trying to decide what the likelihood of finding life in the universe is. Now, there has been a recent announcement from scientists, maybe it was 2 years ago now, 2018, I think, who have been analyzing and trying to understand the properties of the planets in the Trappist system. So they look at the transits, they look at the light that's getting from the star, they determine the habitable zones, they imagine the density of the planets, they do all those sorts of things. And they think Trappist 1e, which is right here in the middle of this group, is possibly an Earth-like ocean world, as they say. That means that they think it's likely or possible that there is liquid water on the surface of that planet. So that's a very exciting development. That is something that's going to require lots more exquisite observations to confirm, but if true, it would be the first world that we think that is true for. So if you go reading the news about Trappist 1, you will first hear about the large number of planets, and then the second news cycle was about the possibility of there being a water world there. Okay, so those are a couple of systems for you to think about. The Exoplanet Catalog is enormous. There's a lot of space there for people to do some exploring and find out what sorts of things we know and what sorts of things we don't know. Next lecture, we're going to talk about the architecture of all these different systems, because one of the questions, outstanding questions we have, is whether or not the way the Earth's solar system is put together is the common way that planetary systems appear, or if there are different norms when we look at all the planetary systems that we've discovered. That's an open question, and it's something that our thinking is evolving with. So we'll talk about that during next class period. Okay, so I hope you're all doing well. Please take care of yourselves, be safe, and we'll talk to you again soon.